At what point should we just admit defeat and give up on our search for dark matter? Should we be sending a lot of cheap space probes instead of a single expensive one? If the universe is rotating, where is the axis? And in our Q&A Plus version, how to make a friend fall in love with astronomy. Answering all these questions and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I'll answer them here. All right, let's get into the questions. Tyler, does a space probe have to cost millions or billions of dollars to gather extremely valuable data? Have we ever sent a swarm of cheaper probes out into deep space on a single mission? So spacecraft can cost all kinds of things, from tens of thousands of dollars, little CubeSats, to millions to billions of dollars, depending on the size, the mass, the complexity, the amount of scientific instruments that are built into it. You know, on the expensive end, we have something like, say, the James Webb Space Telescope, which is like one of the largest satellites that's ever been launched. Took one of the most powerful rockets to launch it, and the thing cost $10 billion. It took 20 years to build. But on the other hand, there are CubeSats. There are these tiny little satellites that weigh just a couple of 100 grams, and they can be built by a university, and they can be tucked into small areas inside larger rockets that can be launched as part of the launch. And the launch costs of that are very inexpensive. And so there are people probably watching this right now who are at a university, and their university is working on a CubeSat. And these CubeSats can do incredibly valuable science. You can put cameras on them. You can put instruments that can measure in various wavelengths. You can have little telescopes on these CubeSats. And so depending on the scientific question that you're trying to answer, you launch the satellite that you need to build. And for some, it has to be this giant flagship. But often, if it's easier to use a smaller one, then you can. And a lot of the times, these CubeSats are used to test out ideas. So, you know, for you to be able to get a mission launched, a big flagship that's going to use some new piece of technology, you have to decrease the technical risk on your mission. So you have to take what is something that's never been flown in space before, and you build it into a CubeSat, and then you launch it for, say, $1 million. You test to make sure that this technology works and it does what you're looking for and proves, it's a pathfinder that proves that your ideas work, and you have then reduced the technical risk. You can then build that instrument into your $1 billion spacecraft, and everybody thinks that you're not being overly risky. So no, we're at this age now, thanks to miniaturization, thanks to decreased launch costs, that you can, you could probably put a CubeSat into orbit for $100,000 all in. The thing would weigh 100 grams, and it would be a fraction of a couple of centimeters across, and yet, you probably could do it. Nithin Cleetus, is there any evidence to show if the universe is rotating? And if that's the case, wouldn't that mean that there is an axis or point around which the universe rotates? So this is based on a recent report where a team of astronomers proposed that the reason we have the Hubble tension, the difference in the measurement of the expansion rate of the universe from a more sort of recent past area around us to the cosmic microwave background radiation, is that in fact the entire universe is rotating. And so that would add an outward acceleration to objects that are the farthest away from us. And then that would partially or maybe even fully explain this Hubble tension. And, once you say, well, if the entire universe is rotating, then you've got to say sort of like rotating around what? What does it even mean for an entire universe to rotate? What if the universe is infinite? What does that mean? And in fact, the astronomers propose that it takes like 500 billion years for the universe to fully rotate once. Again, what does that mean? So I'm not going to answer your question, unfortunately, but I'm going to direct you to Dr. Becky's video. So she did a recent coverage of this, and then she also posted a short where she answered this exact question. And the gist, if I remember her answer, is that it's sort of like, there is no reference point, that, if the universe is finite, then there still is no center of the universe. And so it's always based on your perspective, where you are, what you see is rotating. But definitely check out her videos in her short to find out a better answer. Trinidatt. Fraser, I'm curious if you can explain to me about gravitational lensing. What are the requirements? Like, how far does the first object need to be, and how much gravity does the observing object need? So gravitational lensing works when you've got a foreground object, a galaxy cluster, a star, a black hole, and then you have a background object, another galaxy, another star, a planet, whatever. And then you as the observer, you are perfectly lined up so that you've got the gravitational lens, and then you have the object that is being lensed. And there's a ton of parameters, but the key is that they need to line up very well. When I say very well, it sort of depends on the lens. If it's a star, then the lineup needs to be really perfect. U, star, target. But if it's a galaxy cluster, the lens can be kind of messy. U, cluster, stuff on the other side of it that looks into these, becomes these crazy arcs around the gravitational lens. But the key is that the gravity, you want more gravity, more better. And so, we talk about this idea of using the solar gravitational lens here in the solar system to be able to observe exoplanets with high resolution. In this case, you need to go out to the solar gravitational lens, which is more than 550 astronomical units away from the sun. And when you get to that point, then you are far enough away that the gravity of the sun is focusing the light like a telescope, and you are at the focal point, and you are then looking at whatever is exactly on the opposite side of the sun from us. And it can be far away. Like, it doesn't matter. The distance doesn't really matter at this point, as long as you're at the focal point. It's kind of the same as you like using a telescope. You move the focal point of the telescope back and forth inside the telescope, and that focuses the light of distant objects that you can see through the lens. So the thing that matters is that more gravity, more better. And so people always suggest, could you use Jupiter as a gravitational lens? And theoretically, sure, you just have to go much, much farther away. That if we had a black hole with 10 times the mass of the sun here in the solar system, then the black hole gravitational lens would be a lot closer. So there's a lot of factors that go into it. And, they're very useful because they provide these natural telescopes. If you want to observe the most distant galaxies, the earliest times in the universe, you've got to use the additional magnifying power that comes from these gravitational lenses to look even farther back. They can take what would be, almost impossible even for James Webb to see and become a galaxy that can be easily studied by James Webb. So, gravitational lenses are vital for astronomy, especially if you want to see stuff that's at the very limits. There's a lot of other cool stuff they do with gravitational lenses, discovering exoplanets, finding, potentially, counting how many rogue planets are out there in the Milky Way, searching for potential primordial black holes. So they're have become just this incredible tool for astronomy. Estraume. Are there any updates on the concept of ion engines for low-flying satellites fueled by gas collected from the upper part of the Earth's atmosphere? So this is an idea of an air-breathing ion engine, and I've done an interview on the channel, and we've done a bunch of stories on Universe Today about this, and this is the idea that, instead of carrying your propellant on board, if your satellite is flying at a low enough orbit, then you could scoop up particles of the atmosphere, use solar energy to ionize them, and then fire them out the back of your spacecraft at really high velocity, like 10,000 kilometers per hour. And then that would give your spacecraft a thrust in the opposite direction. And so in theory, you could scoop up atmosphere as you're orbiting it low enough, and then use that as an accelerant. And you wouldn't have to carry propellant. You would have no fuel on board your spacecraft, just solar electricity, which would be sustainable. And people are trying to figure out a way to make this work. That we're currently in the engineering stage. Some people think the math holds and that this would work. It might work in better other worlds, like it might work on Venus or even on Mars, Titan. So stay tuned. It's an idea that I'm really excited about. And so I'm always watching for anyone to have made a practical improvement. But the interview that I talked about, it's all still kind of in the theory and engineering prototype phase right now. So no updates. It's time to shout out our new patrons at the $5 level and above. Daniel, Jerry Mars, Dave, Marbo, Christian Bennick, Philip Stanford, Charles Belinsky, Joseph Torre, Trina, and Margaret Feaster. Join our community at patreon.com/universetoday. Andreas Lusti. Hey Fraser, I always wondered if it's always you who reaches out to interview candidates, or are serious researchers already queuing up to get an interview slot with you? It's always me. It is 99% me. And the way this works is I go through my review of all of the literature every day. So I go through all of the journals, all of the press releases, all the research that's coming out from NASA, and I have this sort of list in my brain of stuff that I feel I don't know as well as I would like to, or stuff that I'm curious about. And then if a piece of research matches that squishy list in my brain, then I'll go, I'm going to try and interview this person. And then I do a bit of research, find out who they are, find out their email, send them an email. Hi, I'm Fraser Cain. I'm the publisher of Universe Today. I saw your recent journal article about using electrostatic surfaces to repel Martian regolith, and I was wondering if you would be available for an interview on my YouTube channel. Here's my YouTube channel. Let me know if you'd be interested, and I will give you a link to my calendar to set a time that works for you. That's the gist of the email that I send out. And I get about a 50% hit rate on that email that I send out. In some cases, it has to go through the press officer for the institution. In really extreme cases, like NASA, they will sometimes want to have a press officer sitting in the conversation while I conduct the interview. And then I get the interview. And, interviews do come in other ways. So I will get like an inquiry from a publicist when there's a new book. So which is, great. Like, for example, I interviewed Eric Berger. He is one of my favorite space journalists, and he had recently written a book about SpaceX. And so his publicist reached out to me and said, hey, do you want to interview Eric Berger? I'm like, yes, please. And so I responded back and said, yeah, I'd be glad to interview him. And like, that's a great time. People who I find are difficult to interview, but if they write a book and they're promoting it, then they're open to interviews. Not that Eric Berger has ever been a problem to interview. He's a star, but if you want somebody who is maybe more difficult to interview, some of the biggest celebrities I've interviewed have come through that process. And then there's been occasionally, and you will see some of these interviews here on the channel, someone who is working on something and is a fan of the channel. Will, they go, you know what, the work I'm doing is interesting enough. I'm going to reach out to Fraser and see if he'd be willing to do an interview about it. And that's great. I love that because they know the format. They know the kinds of questions that I ask. They understand what my level of technical ability is and the kind, they know where I'll try and set the interview level at. And often those go very well. I'll do some vetting to make sure they are who they say they are. And I look at their research and get a sense of what the story I think is, and we'll conduct the interview. But I would say it is 95% of the interviews are me cold calling researchers based on work that they've done. And in many cases, it's their first interview. They've never been interviewed before because nobody has ever bothered to reach out to them because everybody wants to talk to, Bill Nye. Frosty Winnipeg, when is Fraser getting an asteroid named after him? I already have an asteroid named after me. The name of it is asteroid 158092 Fraser Cain, and I have had the asteroid for more than a decade. So, for those of you who don't understand how this works, when you discover an asteroid, you are able to give it a name. You can make a recommendation of a name to the International Astronomical Union. And they have various qualifications about the size that the names can be, and you can't use dirty words and all that kind of stuff. But you can name them after people. And so back about, like 15 years ago, there was an astronomer named Jeff Metcalf. And he was called the blue collar astronomer. And he was a sort of prolific asteroid hunter and named asteroids after a lot of people. And I got one, Derek Colanduno got one. So there's a bunch of them were given out. So it's early in the skeptic movement back in the sort of early 2000s. But there's been a lot more asteroid hunters that have been naming a bunch after people recently. And so I know Anton Petrov just got an asteroid. So congratulations, Anton. And I know Brady Haran got one as well. Now Brady got the biggest one and he just lords it over all of us. But it's great. It's amazing. What an honor to have an asteroid named after you. Of all of the legacy, of all of the things, at some point in the far, far future, when humanity spreads out into the solar system and begins dismantling the solar system, at one point they will get to asteroid 158092 Fraser Cain. They will dismantle it and they'll pour one out, I hope, as they are tearing it apart to build their Dyson swarm. So thanks to Jeff Metcalf. Now, the The tragedy is that Jeff Metcalf died of cancer, in his early 40s. So shortly after he was giving this incredible gift to all of us science communicators, giving us asteroids, he passed away, and it really sucks. So, if you want to participate in this process, get out there, discover asteroids, name them after people who you think should be remembered in history. And I can't believe one of them is me, but yeah, I have an asteroid named after me. Maciej Jurkowski, how long do we search for dark matter until we just admit that it really is a particle that is not interacting at all except via gravity? I don't know if anyone would ever say, okay, we just have to admit that it's a particle that is not interacting except by gravity, because that, as long as you don't know what it is, then there are still various possible theories that explain what dark matter is. Like, all we have are the collection of observations that galaxies are rotating in strange ways that don't match the way you would expect the stars in a galaxy to rotate, that galaxies should be tearing themselves apart the way they rotate, that we see gravitational lensing at the largest scales when there seems to be nothing there that is actually producing the gravity that's causing the lensing, and that we can measure the ratios of matter to other things in the early universe and the cosmic microwave background radiation, and that these and other observations build together to create this case that there is more to the universe than we can see. That is dark matter. Dark matter is the collection of observations that have been made that the universe behaves in ways that our current laws of physics, as we understand, don't predict. That's it. That's the beginning and the end. Now, obviously, when you say, like, we've got a mystery in our hands, the universe is not behaving the way we expect, the first thing to say is, well, maybe we don't understand how the universe should be behaving. Like, obviously. And so there are certain theories for dark matter that say we don't understand how the universe is actually supposed to work, only what we think it's supposed to work. And that's like one group of theories to explain it. Another one is like, maybe there are invisible particles that we can't see, and that would explain it. And like, that's another one. Or maybe our measurements are off, and that's another possibility. And so I don't think, like, until somebody like actually produces dark matter particles in a particle accelerator like CERN, or makes an observation where they can detect the particles interacting in a way that really is a smoking gun to say, okay, yes, fine, it is particles that is causing dark matter, then the controversy will never end, because it won't be a completely satisfying answer for the entire scientific community. You're always going to have factions. One group says it's got to be this, one group says it's got to be that, and neither has enough evidence to make a compelling case that everybody will agree on. But we see this all the time, right? This is science, that there are various states of scientific theories, from I've got a rough guess to the theory of evolution, right? That is well established with hundreds of lines of evidence that nobody who understands the current level of the science would have questions about the main ideas, and is then going to be arguing about different parts of it. So dark matter is just earlier on that process to go from collection of observations to a comprehensive theory that helps us understand it. And until we get to comprehensive theory, then it's really open season for everybody. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus, and this week's bonus question is all about how to help a friend fall in love with astronomy, and I'll put a link in the show notes. All right, those are all the questions that we had for this episode. Thank you, everyone who asked your questions in the YouTube comment, and everybody who asked your questions during the live show, which is 2 hours long, and we record every Monday. The next one is in Pacific time. The next one after that is in Australia time. The next one after that is back to Pacific time. So it rotates. But yeah, come. It's 2 hours long. Lots of great questions and answers. I think you'll really enjoy it. Now, I'm going to talk about my long-running collaboration, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, David Gilton, and David Matz, Dustin Cable, Evan Pro, Greg Feely, Hans Schultz, Hudson Ward, Jay Graves, James Clark, Jerry Mattern, Jim Burke, Jordan Young, Marcel Smits, Michael Purcell, Modzo, Paul Robach, Rank Kaidu, Robeck, Sean Sargent, Stephen Fowler-Munley, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So for those of you who are watching my YouTube channel, you might be familiar that I am the publisher of the Universe Today website, which is one of the most popular space and astronomy news websites on the internet. And thanks to you, it has no ads on it. But I am also the co-host of the Astronomy Cast podcast, which is a long-running podcast on space and astronomy that I do every week with my co-host, Dr. Pamela Gay. And we have been doing this show since Pluto became a dwarf planet. So 2007, I think, and we're up to episode 759 at the time that I'm recording this. And so if you want like really interesting explainers on different topics in space and astronomy, which are sort of like soup to nuts about supermassive black holes or gamma ray bursts, each episode covers a different topic. And so if that's the kind of thing that you're interested in, you should definitely check out Astronomy Cast. Now, we do that show live here on YouTube as well. The recording of the entire show takes about an hour. We do that on Mondays at 11 a.m. Pacific time. And you should come check it out, hang out, ask questions there. It's a really good time. All right. Check out Astronomy Cast, subscribe to it wherever you get your podcasts. A huge thank you to my collaborator, Dr. Pamela Gay, and we'll see you all next time.